Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 2 on factoring. That's right, factoring, your favorite topic. The topic that you think is probably almost synonymous with math at this point, right? So let's get right into it. A lot of what we're going to do today is going to be review from Algebra 1, but you know, a couple years ago, etc. So let's jump right into it and discuss factoring. Factor, two important meanings. Expressions can be written in equivalent forms in many ways, and we've already seen this quite a bit. When an expression is written in its factored form, we can determine important properties of the expression. It's important to review the two fundamental definitions of the word factor, which you saw in Algebra 1. So let's talk about these a little bit. The two meanings of the word factor. First, factor, a verb. To write a number or expression as an equivalent product, i.e. as an equivalent multiplication problem. Two, factor, noun, one of the individual numbers or expressions that are part of the product. So before we even get into exercise 1, right? If I took the number 12 and I said factor it, and you said, well, 12 is equivalent to 3 times 4, awesome, you have factored the number 12. If I then said, what are some factors of 12? And you said, well, 3 is a factor and 4 is a factor, that would also be correct, right? Because they are part of a product that produces the number 12, all right? So all factoring is it's one of the simplest ideas of all. It's taking a particular number or expression and writing it as an equivalent product. And each part of that product is then known as a factor of the product. And it is kind of confusing because factor verb, factor noun. All right, let's take a look at exercise number 1. Consider the expression 12x squared plus 30x. Using the distributive property in reverse, rewrite the expression in 4 different ways as a product or in factored form. Now again, before we even kind of get into this, I really want to emphasize this, right? The distributive property kind of looks something like this. A times b plus c, and I'll put even a little dot there for times, is equal to a times b plus a times c. And you've heard me say this phrase a lot in the past. Equality is a two-way street. In other words, right, we can say that that is equivalent to that, but then again, we can also go in the opposite direction. And that's exactly what we're going to be doing today as we look to factor these expressions. So keep this in mind, right? Typically, we think about the distributive property and even multiplication as sort of something we're doing to something else. Oh, we're going in this direction. But we can also go in this direction to get something that's equivalent. Anyway, let me get rid of this. So, all right, we want to rewrite this particular expression, 12x squared plus 30x, in 4 different ways. So, let's take a look. At the numbers, we've got 12 and 30, right? And I want to think about, let's say, a common factor of 12 and 30. Well, one nice common factor of both 12 and 30 is the number 6. So I could actually rewrite 12x squared plus 30x. I could write that as 6 times 2x squared plus 6 times 5x. But then, because there's this common factor, I can, quote, factor it out, and I can then rewrite this as 6 times 2x squared plus 5x. So in other words, that is an equivalent way of writing our original expression, but as a product. Now, you might say, well, okay, but there's other numbers that go into both 12 and 30. For example, probably the simplest number that goes into both of them is 2. Right? So another way to factor this is I could say, well, 12x squared plus 30x would be equal to 2 times 6x squared plus 2 times 15x. And therefore, because I've got a 2 sitting here and a 2 sitting here, I could rewrite this by running that distributive property, quote, backwards as 2 times 6x squared plus 15x. Now you might notice, of course, that both the x squared and the x have an x in them, right? Let me just box this in as well. So I could say, well, you know, then maybe I should, quote, factor out an x. In fact, right, I could rewrite 12x squared plus 30x. I could rewrite this as 12x times x plus 30 times x, right? We have an x sitting in both of those slots, so I could rewrite this as x times 12x plus 30. So that's a third equivalent way of doing it. Pause the video right now and see if you can come up with at least one more, if not a few more ways of writing this as an equivalent product. Pause the video now. All right, well, there's a lot of different ways, and many of them involve both using the x that we had here plus another number. So for example, another nice one would be to say something like, well, I can take both 12 and 30, and I know 3 goes into both of them, and maybe I'll have that x come along for the ride. I could write 12x squared as 3x times 4x, and I could take 30x and write that as 3x times 10, right? So I have this common factor now of 3x. So I could factor the 3x out and have 4x plus 10, right? And there's many different ways to do it, right? Because I can combine sort of a numerical coefficient along with that variable x and keep factoring it out, right? But here are 4 ways of doing it. All right, let's continue talking about what's called greatest common factor factoring. So factoring out a GCF. The type of factoring in the first exercise is often referred to as factoring out a common factor, right? There's a common factor for both parts of those binomials that we looked at. Most of the time, we want to be able to factor out the greatest common factor, the biggest thing that we can possibly factor out. So let's take a look at that process in exercise number 2. Write each of the following binomials as the product of the binomial's GCF and another binomial. All right, so let's talk about this term greatest common factor. Now, when we're looking at this, what we always want to do is we want to look first at the numerical coefficients that are showing up in our expression. So in letter A, we have 3x squared plus 6x. All right. Now, what I know for certain is that both the 3 and the 6 have a largest common factor of the number 3. The number 3 is the largest number that will divide into both of them. But we also have an x squared and an x, so there's also a common factor of x. So in this particular case, our GCF is 3x. Now, using the same kind of process I did in the last problem, I can think about 3x squared plus 6x as 3x times x plus 3x times 2, right? There's that greatest common factor. And then I can, quote, factor that out, and I can rewrite this as 3x times x plus 2. All right, I'm literally just identifying the biggest thing that I can have. And by the way, I know that 3x is the biggest thing I can have because when I look at the parts that aren't involved in the 3x, i.e. the x and the 2, they don't share any common factors, right? If I've not gotten the greatest common factor out, then what's sort of left behind, if you will continue to have common factors to it. Let's take a look at letter B. Here we have 20x minus 5x squared. Yet again, what I want to do is I first want to consider the number 20 and the number 5. And I want to say, well, what is the largest number that will divide nicely into both of them? And that's the number 5. Okay, great. But as well, just like before, we also have an x and an x squared. See if you can use the fact that the GCF of this particular expression is 5x to write it in its factored form. All right, well, I'm going to kind of keep doing this process for a little bit more because I think it really hammers home how we're reversing the distributive property. So I can rewrite 20 times x as 5x times 4, and I can rewrite 5x squared as 5x times x. So I've got that greatest common factor of 5x, and when I factor it out, what's left is 5x times 4 minus x. All right. Pause the video now and see if you can tackle letter C all on your own. All right, well here we look at our 14x to the third and our 21x to the second. Considering only the 14 and the 21, the largest number that divides into both of those nicely is the number 7. We've got an x cubed and an x squared, and so that means actually the variable portion of this that is sort of contained in both of those is an x squared. So our GCF in this case is equal to 7x squared. We could rewrite this as 7x squared times 2x plus 7x squared times 3. Come on, there we go. Get that dot a little bit bigger. So then I can rewrite it as 7x squared times 2x plus 3. All right. Now let's take a look at letter D together. Here we have 30x squared times y minus 20 times xy squared. And it may look a little bit more confusing because we've got two variables here, both an x and a y. But keep in mind that in both of these two terms, 30x squared y and 20xy squared, that's all multiplication, that's all multiplication. So I go through the same thinking process, the 30 and the 20, the largest number that divides into both is the number 10, right? So my GCF is going to contain the number 10. Then I look at my x variables. I have an x squared there, I have an x to the first there. So the biggest thing that both of them will contain is an x to the first. And then my first term's got a y to the first, my second term has a y squared. The largest thing I can do there is a y to the first. And continuing to do this sort of thing where we reverse the distributive property, the first thing I can rewrite as 10xy times 3x minus 10xy times 2y, right? There's that 10xy, that GCF. So then I have 10xy times 3x minus 2y. It wouldn't surprise me at all if many of you, because of Algebra 1 and maybe even some work on factoring and geometry, can actually go from identifying the GCF immediately down to here without writing these lines out. And that's of course okay. There's nothing wrong with that. But I really like to be able to see how we run that distributive property backwards by identifying either a common factor, like we did in exercise 1, or a greatest common factor, like we did in exercise number 2. Let's make sure you have this with a pretty simple multiple choice problem. Bring this up here, and let's take a look at exercise number 3. Rewritten in factored form, 20x squared minus 36x is equivalent to which of the following? All right, pause the video now and see if you can figure out what the correct choice is. All right, well, one way to do this, by the way, right, is instead of factoring, you could write each one of these things out after you've distributed whatever that number is or that expression is outside of the parentheses. That's a fine way to do it, right? And then that will tell you which one's equivalent to this. But let's kind of go in the direction of doing the factoring instead. I've got 20x squared minus 36x. I look at my 20, I look at my 36, the largest number that divides into both, right? If I think that this is a GCF, the largest number that divides into both is a 4. Because we have an x squared and an x to the first, I can pull out a 4x. Now that might be enough if we're going on the premise that this is just a GCF problem. But I can rewrite this as 4x times 5x minus 4x times 9, in which case that 4x can be factored out, and then I have a 5x minus 9. Choice 2. All right, lovely. Let's keep working more with factoring. Factoring with trinomials. We will sometimes need to write trinomials as the product of a GCF and another trinomial. All right, and then we're going to have to maybe even factor the trinomials, but that's for another lesson. Right now, let's just work on that GCF factoring with trinomials. Exercise number 4. Rewrite each of the following trinomials as a product of its GCF and another trinomial. All right, now this is exactly what we just did with binomials. The only difference is we have to consider 3 terms instead of 2 terms. And whatever the common factor is, it has to be common to all 3. Not 2 out of the 3, but all 3. So let's take a look at letter A. Here we have 2x squared plus 8x plus 10. Just like before, the first thing I want to do is consider the 2, the 8, and the 10. The 2, the 8, and the 10 obviously are all divisible by 2. So that's going to be part of our GCF. Now, I consider an x squared and x to the first, and there's no x's there. Since there is no x attached to that 10, x cannot be part of a common factor because it's not a factor of 10, right? So in fact here, our GCF is very simple. It's just 2. And in fact, this trinomial can be thought of as 2 times x squared. Well, that doesn't look like a x squared. 2 times x squared plus 2 times 4x plus 2 times 5, in which case we can rewrite it as 2 times x squared plus 4x plus 5. Simple, right? Why don't you go ahead and do letter B on your own? Now letter B you have to be a little bit careful with. It seems a lot like letter A. We've got 10x squared minus 20x plus 5. Right, we look at the 10, the 20, and the 5. The largest number that divides into each one of them is the number 5. Awesome. Just like before, this has an x squared, this has an x to the first, this has no x's on it, so we cannot include an x. So our GCF is easy enough. It's purely numerical. It's just a 5, right? And we can rewrite all of this then as 5 times 2x squared minus 5 times 4x plus 5, and here's the kicker, times 1, right? So I have 5 times 2x squared minus 5 times 4x plus 5 times 1. So this is all 5 times 2x squared minus 4x plus 1. There we go. All right, that looks a little bit better. Space management, never been my forte. Now, I said you had to be a little bit careful on this, and the reason why is that it's very tempting when people use the phrase factor out a GCF. It's very convenient for people, or very often for students, to say that all of this would become 5 times 2x squared minus 4x, and they wouldn't include the plus 1, right? Now the problem with that is that if this is not included, right, if that's not there, then if you were to distribute the 5 through the parentheses, you wouldn't end up with this. You would end up with the 10x squared, you'd end up with the minus 20x, but the plus 5 wouldn't be there. And therefore, the two expressions would not be mathematically equivalent, right? So you've got to have that plus 1. Never forget that. We are producing expressions that are mathematically equivalent, and because we're factoring, what that means is that if we then go in the forward direction, i.e. we multiply everything out, it has to come back out to what we began with. All right, let's take a look at letter C. We've got 8x cubed minus 12x squared plus 20x. All right, here's an example of one where we have both numerical coefficients and we've got variables in each one of the terms. We look at the 8, the 12, and the 20 and note that the largest number that divides into each of them nicely is the number 4. But they also all have x's on them. X cubed, x squared, x to the first. That tells me that my GCF also contains an x to the first. In which case, I can write down GCF is equal to 4x. Again, this little intermediate step, I'd have 4x times 2x squared minus 4x, maybe I'll get rid of that line now, minus 4x times 3x plus 4x times 5. I'm not going to have any room left for the last one. We'll deal with that when we get to it. So I've got my 4x, and my 4x. And therefore, we have 4x times 2x squared minus 3x plus 5. All right, easy enough. Why don't you pause the video and give a shot to letter D. All right, letter D is very, very similar to letter C. We look at the 6, the 15, and the 21, and we note that the largest thing that goes into each of them is 3. We've got x cubed, x squared, x to the first, so that we also pick up an x to the first. Our GCF is therefore 3x, and I think I'm going to carve out a little space down here for the rest of this problem. Maybe do something like that. So I can rewrite all of this as 3x times 2x squared plus 3x times 5x minus 3x times 7. And therefore, we have 3x, I almost said 3x squared. We have 3x times 2x squared plus 5x minus 7. All right, so factoring at a GCF. That is the most simple of all types of factoring. Now, we are going to look at one more type of factoring in this lesson set, and we'll get to it right now. But we'll also see how to factor trinomials in our next lesson. We'll see something like factoring by grouping in the lesson after that. So there's going to be some cool factoring techniques we're going to look at coming up. This is pretty basic. There are many types of factoring, but all of them achieve the same purpose: rewriting an expression as an equivalent product. Another type of factoring you saw in Algebra 1 was based on the product of conjugate pairs. Now, conjugate pairs are a funny word, but they come up a lot in mathematics, okay? And what a conjugate pair is it's a pair of binomials that looks exactly the same, but one of them has addition and one of them has subtraction. So x plus 5, x minus 5, 9 plus y, 9 minus y, 3t minus 2, 3t plus 2. A minus B, A plus B, right? They all have this structure where they have exactly the same two terms, but one of them has the terms added, one of them has the terms subtracted. Now, in exercise 5, what we want to do is we want to go in the quote forward direction. We'd like to multiply these out, okay? So let's take a look at letter A first, and I think I'm going to multiply each of these out by using the FOIL method simply because it's the quickest method. Let's take a look at letter A real quickly. We've got x plus 5 times x minus 5, and I just want to find that product. I want to multiply it all out. So, simple enough, if I use the FOIL technique, which says multiply the first two terms, I get x times x, which is x squared. Then I'm going to have my outer two terms multiply. That's going to be a negative 5x. I'm going to have my inner two terms multiply. That's a positive 5x. And then a 5 times negative 5 is negative 25. And notice what happens is that normally when we multiply two binomials, that outer and inner term combine and leave you with something to the x to the first. In this case, a negative 5x and a positive 5x cancel, and it just leaves us with a binomial, which is a little bit strange. Most of the time, when we multiply two binomials together, we get a trinomial at the end. But in this case, right, the O and the I terms of FOIL, if you will, canceled each other and just left us with x squared minus 25. What I'd like you to do now is pause the video and do all the rest of them. All right, I'm going to go through exactly the same process, but a lot faster now. In this case, I had to have 9 times 9, which is 81. Then I'd have 9 times negative y, which is negative 9y. 9 times positive y, positive 9y. And y times negative y squared. And again, the negative 9y and positive 9y cancel, and I'm left with 81 minus y squared. And that keeps happening, right? In letter C, I have 3t times 3t, which is 9t squared. 3t times positive 2, which would be positive 6t. Negative 2 times 3t, which would be negative 6t. And negative 2 times positive 2, which would be negative 4. Somehow, the 6t and the negative 6t cancel, and I'm left with 9t squared minus 4. And finally, the most general case, a minus b times a plus b. A times a is a squared. A times b is, well, a times b. Negative b times a, remember multiplication is commutative, so I can rewrite that as negative a times b. And then negative b times positive b would be negative b squared. Positive ab, negative ab cancel, and I'm left with a squared minus b squared. So what we see is whenever we have a product of conjugate pairs, instead of getting a trinomial at the end, we have our outer and our inner terms of foiling canceling each other out, and we're really left with the first part of the binomial squared minus the second part of the binomial squared every time, right? And of course, if you recognize that pattern, then multiplying two conjugates is very quickly, because you square the first portion, you square the second portion, and you subtract the two. And that's exactly what we've got going on here, product of conjugate pairs. Two binomials are conjugate pairs if they contain the same terms, but one has addition and one has subtraction. The following will always be true. x plus y times x minus y equals x squared minus y squared, and importantly, right, equality, two-way street, x squared minus y squared is equal to x plus y times x minus y. Now again, I'm emphasizing equality, two-way street, really important idea here, because we're factoring today. You know, that was not factoring what we just did. That was sort of the reverse direction. That was multiplying. But what we want to now do is we want to take expressions that look like this and we want to turn them into expressions that look like that. So let's do that in our next set of problems. The difference of perfect squares. We can reverse the previous type of products when we recognize that an expression has the structure of the difference of perfect squares. In other words, right, that's exactly the same box we had before. We have some quantity squared minus some other quantity squared. And the difference of perfect squares, that name says it all. It's a difference. There's got to be subtraction. And it's got to be the difference between some quantity squared and another quantity squared. Let's take a look at that in exercise number 6. Write each of the following binomials in its factored form. All right, well, this really requires us to look at x squared minus 9 and say, oh, x squared minus 9, that is the same as x squared minus 3 squared, right? So I recognize that 9 is a perfect square. And because of that, I can write it as, 3 squared. Now, as soon as I recognize this fact, then I can use what we just saw, which is that anything that looks like this, something squared minus something squared, right, can be written as x plus y times x minus y. Well, this can now be written as x plus 3 times x minus 3. Really, really quite simple. And if we wanted to prove it to ourselves, we can multiply it all back out and we'd get x squared minus 9, but there's really no need to do that, okay? Now, you know, you might look at something like 4 minus n squared and think, oh, n plus 2 times n minus 2, because I see a 4, I see an n, I see a subtraction, all of that. But keep in mind, right, 4 minus n squared, that can be thought of as 2 squared minus n squared, and then that's going to be 2 plus n times 2 minus n. Okay, so you do have to be a little bit careful. In subtraction, order matters. Addition, it doesn't. So if I made this n plus 2, that's cool. But that can't be n minus 2. That would be a problem. All right, let's take a look at one more, and then we'll have you do one on your own. 4t squared minus 25. Now that's a little bit more challenging, but keep in mind that 4 is a perfect square, t squared is a perfect square, there's a difference, and there's a 25. Now again, I have to be a little bit more careful here, right? We really want to think about this as 2t squared minus 5 squared, in which case all of this becomes 2t plus 5 times 2t minus 5. All right, what I definitely don't want to write down is 4t plus 5 times 4t minus 5, because when I multiply those two out, I would get 16t squared and not 4t squared. I gotta really be careful about that. All right, why don't you try letter D on your own? Letter D is quite similar to letter C. I've got 16 minus 81y squared. 16 and 81 are perfect squares. 16 is 4 squared, and 81 is 9 squared. So I can think of this as 4 squared minus the quantity 9y squared, in which case this is going to be 4 minus 9y times 4 plus 9y. Now I'll definitely get some students that'll say, well, I wrote 4 plus 9y first and then 4 minus 9y second. Are those the same? My answer is absolutely, absolutely. And by the way, if you've got that question, good for you, right? You know, because sometimes I write the plus first, like I did in all of these, and then this one I changed it up. Not even on purpose, just because I'm inconsistent. All right, but it doesn't matter because, of course, multiplication is commutative. So whether you have this quantity times this quantity or this quantity times this quantity doesn't make a difference. All right, let's take a look at letter E, F, G, and H, which can be a little bit more challenging, especially E, F, and G, because they involve fractions. What I don't want you to forget, though, is that when you multiply two fractions, like, I don't know, let's say 1/3 times 1/3, right? When you multiply two fractions, you always multiply the tops and you multiply the bottoms, all right? And maybe I should have said, maybe a better example would be 2/3 times 2/3, which gives me 4/9. All right. In other words, you know, if you're squaring or thinking about the square root of a fraction, either way, you simply think about the square root of the numerator and the square root of the denominator. So when I see something like x squared minus 1/4, right? Well, 1/4 can be thought of as 1/2 squared, right? So this is all x squared minus 1/2 squared. So that's going to be x minus 1/2 times x plus 1/2. Easy. Why don't you go ahead and try letters F, G, and H. Now I know H, you know, was the kind of full thing, but at least it didn't have any fractions in it. It did have two variables, but you know, no fractions. So letter F, right? I can think of letter F as 5 squared minus c over 3 squared. So that's going to be 5 plus c over 3 times 5 minus c over 3. Letter G, I can think of this as 2/9 times x squared minus 7/3. This one's really ugly, squared. So I've got 2/9 x plus 7/3 times 2/9 x minus 7/3. Now, letter H, there's really no issue with those extra variables. I can think of 36x squared as the quantity 6x squared. I can think of 49y squared as the quantity 7y squared, in which case all of this becomes 6x plus 7y times 6x minus 7y. All right, fantastic. Difference of perfect squares. Very important type of factoring. We now have two types of factoring, right? We've got our GCF factoring, or just common factor factoring for that matter, and we have difference of perfect squares factoring. We can combine those together and talk about what's known as complete factoring. Factoring an expression until it cannot be factored anymore is known as complete factoring, and you've done this for years. Way back even before middle school, you were completely factoring whole numbers. All right. In general, when completely factoring an expression, the first type of factoring to always consider is that of factoring out a GCF. So if you ever see a problem that says factor the following completely, then the first thing I want you to always look for is a GCF. Because if there is one and you factor it out first, it will make your life easier in the long run. Let's take a look at exercise number 7. Using a combination of GCF and difference of perfect squares factoring, write each of the following expressions in its completely factored form. Awesome. So again, completely factored, right? That right there, completely factored form. And what that means is the first thing I'm going to do is I'm going to look at an expression in letter A, which is 5x squared minus 20. I'm going to think about the 5 and the 20, and I'm going to go, oh, biggest number that divides into both 5 and 20 is 5. So I can rewrite this thing as 5 times x squared minus 4, right? And that's just GCF factoring. And then what I can do is I can look inside of that parentheses and I say, oh, x squared minus 4. That's the difference of perfect squares, right? That's x squared minus 2 squared. I'll omit writing down that portion. But then that becomes 5 times x plus 2 times x minus 2. Don't lose the 5. Some students think that when you factor out a greatest common factor, it just sort of like goes away, just flies away into the wind. The problem is, remember, we're trying to write equivalent expressions, things that are the same, right? And if I said factor, let's say the number 12, and you said, oh, the number 12 is 2 times 6, but I'm going to just let the 2 fly away, Well, then you'd be saying the equivalent of 12 is equal to 6, right? So if suddenly this 5 just vanishes because you're like, well, it's a 5, it's a number, I don't need that, I just need the variables. No, that's a problem, right? Without the 5, I could never get back to this. All right. Well, what I'd like you to do now is pause the video and see if you can do this. In each case, what's going to happen is you're going to be able to factor out a GCF, and what remains will be able to be factored with the difference of perfect squares. So practice on that on the last 3 of them. All right, well, letter B might be the most tricky of them all. It's easy enough to look at the 28 and the 7 and say, well, the greatest common factor is 7. But the first thing you got to make sure of is that when you factor that 7 out, you're left with 4x squared minus 1 inside of the parentheses and not just 4x squared. Again, without that minus 1, there's no way you'd get back to here. Now, when I look at 4x squared minus 1, I note that 4x squared is 2x times 2x, and 1 is, of course, 1 times 1. So I can rewrite all of this as 7 times 2x plus 1 times 2x minus 1. All right. Letter C. Now I'm looking at both a 40 and a 250. And I'm thinking, what is the biggest number that divides into both of those? One thing that's obvious actually is the correct choice, and that's the number 10. So I can factor out a 10 from both of these, and I'll be left with 4 minus 25x squared. And I like that because both the 4 is a perfect square, it's 2 times 2, and the 25 is a perfect square, it's 5 times 5. So, making sure I don't lose the 10, right, I can rewrite this as 2 minus 5x times 2 plus 5x. And there's my answer. Now, letter D might seem a little bit more dicey because we have an x to the third and an x to the first, right? First, to begin, right, 3 and 48, the biggest number that divides into both is a 3. Okay, so great, that's part of the GCF. But because I have an x to the third and an x to the first, I can also factor out an x to the first. So I begin by rewriting this as 3x times x squared minus 16. Now what remains inside of the parentheses is the difference of perfect squares, so I can write this as 3x times x plus 4 times x minus 4. And that's it. All right, we have it. Let's summarize the lesson. All right, so today we talked about factoring, and we didn't probably talk about anything that was absolutely brand new to you. It might be buried a little bit deeply in your Algebra 1 knowledge, but it's there, right? Factoring is the process of breaking an expression, a mathematical expression, or just a simple number, into an equivalent product. A product that if you multiplied it back out would give you what you started with. And it might seem a little bit strange that we learn how to sort of go backwards in math from multiplication, how to take sort of, if you will, an answer, here's a product, and reverse it, right, so that we actually come up with the things that are in that product. But factoring has a myriad, a plethora, or any other SAT word you want, number of uses in mathematics. In fact, it's what I would call a gateway skill in mathematics, in that it's so important that if you cannot master it, it really closes the door to many other types of problems in math. But don't worry, we're going to spend quite a few lessons in this unit kind of reviewing and learning new types of ways to factor. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.